Hello and welcome to the IPOS IT Law Series 2022. This is the introductory lecture, Digital Computing 101. A short introduction about myself. My name is Khang and I'm an assistant professor of the SMU Yongpang House School of Law and the School of Computing and Information Systems. And I will be your speaker for today's lecture. In this lecture, I will be introducing you to the following topics. First up, computer systems and digital technologies. Next, we have algorithms, programming and software, followed by networks and distributed architectures, and finally, we will cover cryptography and security. The goal is to cover the basics of these computing technologies that are powering some exciting new developments, such as the metaverse, the use of artificial intelligence, and of course, the blockchain. So let's begin with the question, what is a computer system? There are a few different ways to answer this question, but at the most abstract and general level, a computer performs a certain function, which is to receive input, process data, and create output, which can either be saved or transmitted somewhere. Looking back in history, there were attempts to design and build mechanical calculators that one might consider to be early analog precursors to modern computers. And during the period surrounding World Wars I and II, the term computer in fact referred to a human job that was performed mostly by college-educated women. The modern computer, however, is electronically powered. It operates on numerical data represented as digits, hence the word digital. And most of the computers that we are familiar with are general purpose, meaning that they can load and run different programs or instructions, as opposed to special purpose computers that can only perform a specific set of instructions repeatedly. And computers also come in different scale and sizes, from smartphones that fit into your pocket to supercomputers the size of a few tennis courts. So we know that the modern computer works on digital data, and very simply, digital data is just a sequence of discrete values as opposed to an analog signal that takes a continuous form. Digital data is represented in binary form, or zeros and ones, sometimes called bits, and can be transmitted electronically using different voltage levels or transmitted optically using light pulses. All analog data can be converted into digital form through a process of sampling and quantization. And bits can also be grouped into larger units, such as kilobits, kilobytes, megabits, and megabytes. And do note that a kilobit is not the same as a kilobyte. Now, with all these ones and zeros, we need to structure all that data in a way that allows humans and computers to work on the data in a meaningful manner. This is where standards like file formats come in. A file is a self-contained resource that holds some meaningful information. For example, it could be a PDF file with pages of formatted text and tables and diagrams, or a video file containing audio and a sequence of still images, or a zip file that contains a bundle of compressed files. File formats can be open or proprietary. And in the world of computers, there is a distinction between software and hardware. Hardware represents the physical, material components of the computer system, whereas software represents the non-material components. Software includes firmware, which refers to software that are critical to the operation of the hardware, usually embedded on the hardware itself. System software, such as operating systems, and also application software, which include the programs that we human users typically run when we use a computer. So the modern computer typically has the following hardware components. First, there is the central processing unit, or CPU, essentially a tiny integrated circuit with billions of transistors, and it performs arithmetic, logical operations based on instructions given to it. One thing to note is that different CPUs may implement different instruction sets. Next, there is memory, which can be read-only or read-access. And this is transient storage space that the computer uses to load instructions and data for immediate use. Sort of like paper a human might write on when working out interim calculations by hand. So computer memory is transient in that they are emptied or lost when the computer is powered down. So to persist or to save information and data, for persistent storage, hard disks are used. Sometimes this is also called secondary storage. And there is also a motherboard that connects all the different components of the computer system together, including connecting the power supply and the input-output devices. Now that we have briefly described what is a computer, our next focus is on algorithms and software. So a formal definition for an algorithm is a well-ordered collection of unambiguous and effectively computable operations that, when executed, produces a result and halts in a finite amount of time. So in other words, an algorithm is a description of a solution that can effectively be executed by a computer. And usually an algorithm is intended for other humans, so it can be expressed in any form that another human would understand. This include pseudocode, natural language, mathematical notation, graphics, flowcharts, and diagrams. While algorithms are intended for a human audience, programs are written for the purpose of being computed. One could then say that a computer program is the implementation of an algorithm in a particular programming language. Programs are typically written and expressed in a high-level programming language, and this written form of the program is also known as the program's source code. Programs may sometimes be written in something else called assembly code, which is a lower-level form of code that corresponds more closely to machine instructions. And the main difference between high-level and low-level programming is in the amount of abstraction that the language offers. Higher-level languages are easier to use and result in fewer human errors because they abstract away a lot of the detailed instructions. After the source code is written, it needs to be built into an executable program. For programming languages like C and C++, this is done by a compiler and linker. The compiler compiles the source code into object code, and a linker links the object code files into an executable file. If you recall a few slides earlier, I mentioned that different CPUs might implement different instruction sets. So when compiling source code, the compiler needs to be told which instruction set to follow, and this makes the compiled program machine-specific and is now tied to a particular instruction set. So to avoid the issue of machine-specific programs, some programming languages use an interpreter to directly execute source code. This skips the build phase entirely, so no compiling and linking. This does result in a slower program, but it allows for increased portability between machines. And sometimes to balance between speed and portability, some programming languages use a hybrid approach, which is to compile source code into an intermediate form called bytecode. And this bytecode is then run by pre-installed virtual machines. And operating systems are a form of system software, and they are very important because on a computer system, they manage the use of hardware and devices, and they're also responsible for managing the execution of programs by the CPU and for allocating resources. So once a program has been loaded into memory and is being run by the operating system, we refer to the program as a computer process. And all these processes are managed at the operating system level. And you can see what processes are being run on your operating systems. For example, if you use Mac OS, you can monitor them using the Activity Monitor app. Or if you're using Windows, you can see what processes are being run through the Task Manager. So for human users to interact with computers, there are two main ways to achieve that. One is through a graphical user interface, and the other is through a command line interface. Command line interfaces are harder to learn because the user needs to learn what commands to type, whereas graphical user interfaces provide more intuitive components for interactions, such as swipeable or clickable menus and icons. And obviously, the graphical user interface is something that is preferred by most new users to computers. Software can also interact with other software, and this is done through application programming interfaces or APIs. The reason why programmers and software developers expose a software's functionality to other programs is because this encourages software adoption and allows for integration of different software. APIs are not only used to expose software services, they can also be used to expose data that reside within a database. And APIs can either be public or private. And if they are public, then they are open for other developers working on their own programs to call the APIs. Another important type of software that I want to talk about is built on this idea called virtualization. Typically, when we think about computers, we imagine the personal computer, like a desktop or a laptop, which has its own dedicated hardware components and software that are installed on it. We know, however, that computers can also be much larger physically and contain a lot more computing power, memory, and storage. So these large-scale computers can sometimes be logically parceled into smaller virtual computers or virtual machines on demand, using special software like hypervisor software, so that each user only has access to the amount of CPU, memory, and storage that has been divided and allocated to him. So this is how cloud providers provide compute services on demand. And beyond virtualizing hardware, it is also possible to virtualize desktops, so remote Windows machines, for example, or virtualize operating systems. And now we're going to switch topics to talk about networking and distributed architectures. To introduce computer networks, let's start with the simplest one, a local area network or LAN. A LAN allows connected devices to share network resources such as a network storage device or a printer. So if you have a work computer in the office, it would most certainly be connected to a LAN. And the network may rely on wired connections using Ethernet or wireless connections using Wi-Fi or a combination of the two. To communicate with one another, each device or node on the network needs to be assigned an address. This is usually done dynamically, meaning that the address is assigned only upon a successful connection to the network. So computer networks also exchange data using something called packet switching, meaning that data is first split into packets before they are sent across the network, and then they are assembled when all the packets assembled at destination when all the packets have arrived. What happens when networks connect with other networks at global scale? Well, we get the internet, otherwise known as the network of networks. The internet is an open and decentralized network that provides access to critical services such as email and chat communications and to content on the World Wide Web via web browsers. Internet service providers or ISPs provide internet connectivity to end users and businesses through wired or wireless connections, and also provide high-speed access through fiber optics and 5G. And this is all done through connections via devices such as modems and routers. As the internet is an open and decentralized system, meaning any node or device can connect or disconnect from the internet at any time, the Internet Protocol Suite was designed to handle how data is routed to its intended destination. And this protocol suite includes the use of IP addresses and the domain name system, or DNS. Once a device is connected to the internet, it is assigned a public IP address. This address is called public to distinguish it from the device's private or local IP address, which is used within the local area network. So generally speaking, there will be two levels of routing before a packet arrives at the device that is connected to the internet. First, the packet is routed at the internet level until it reaches the modem or router with the correct public IP address. Then the packet is routed within the local area network until it reaches the device with the correct local IP address. And to find out what is your device's public IP address, you can search "what is my IP address" in your favorite search engine, and the search result would show your public IP address. However, because IP addresses are numbers, they're not easy to remember. To allow easier access to web servers, the domain name system DNS operates to map human-friendly names like, for example, iposinternational.com or smu.edu.sg to their respective IP addresses. So domain name registration is administered by usually by a registry or a registrar, and some of these registries operate to manage country-level, top-level domains. So in Singapore, SGNIC manages the .sg domain names. Now we have the ability to connect computers together in a network. This presents the opportunity to build distributed applications that are more useful than just local applications. Many distributed applications on the World Wide Web are based on the client-server model. For example, when you load a mobile app on your phone or visit a website that requires a login and password, your device acts as a client by running code that creates a connection to a server and sends or fetches data from the server. This separation of work between the client and server can result in better optimization of resources. Another distributed application model that one might have heard of is the peer-to-peer or P2P model. Unlike the client-server model, which centralizes control and resources at the server, the P2P model is completely decentralized, with all the nodes connected to it operating as peers. And all peers are equally suppliers and consumers of resources within the network. For example, in P2P file sharing networks, computers connected to the network allow other users access to their files as well. And the decentralized nature of such networks make it more challenging, for example, for law enforcement to remove illegal content as compared to simply removing files that are hosted on a central server. And blockchain networks, such as Bitcoin, are an example of P2P networks as well. And finally, in this part, I'll be talking about some modern cryptographic methods and their applications. So modern cryptography relies on this thing called Kirchhoff's principle, which says that a crypto system should be secure even if everything about the system, except the key, is public knowledge. Symmetric encryption is a subset of cryptography algorithms, and symmetric encryption algorithms encrypt and decrypt data using a shared secret key. What is a key in this context? A key is just a number. If we recall that computer systems represent data using the numerical form, using the base 2 system in binary. So to encrypt data using a key, what we do is we take the original data, or what we call plain text, which is in numerical form, and transform it into another number using this key. And of course, a series of calculations as well, depending on the algorithm that's used. So this new number is what we call the encrypted data, also known as the ciphertext. And to decrypt the ciphertext back into plain text, we take the same key and we apply a series of calculations to reverse this ciphertext into the original number. And this is how we get the original data back. Symmetric encryption is usually used in combination with asymmetric encryption, something that we will cover in the next slide, because asymmetric encryption provides a secure method to share over a network the secret key that is used in symmetric encryption. Unlike symmetric encryption, asymmetric or public key encryption does not rely on sharing a secret key. Instead, encryption and decryption is done using a combination of two keys, the public key and the private key. The private key and the public key are mathematically linked numbers, and the generation of these key pairs is premised on the intractability of certain mathematical problems. In other words, for such mathematical problems, finding the answer to them requires significant amounts of compute power such that it becomes infeasible in practice to guess the answer. So here in asymmetric encryption, the private key is never shared, and only the public key is announced or published or distributed. And in this example here, Bob uses Alice's public key to encrypt the message before sending the encrypted ciphertext to Alice. Assuming that nobody else knows Alice's private key, only Alice is able to decrypt the message using her private key because of the mathematical relationship between her public key and her private key. So now we have a reliable way to secure data without having to deal with the issue of sharing secret keys, like what we had to do for symmetric encryption. However, asymmetric encryption is slower than symmetric encryption, as the keys need to be longer, because part of it is public now, and the algorithms tend to be more complex. Hence, it is often used together with symmetric encryption for the purpose of encrypting just the symmetric secret key before it is sent over a network. Apart from encrypting and decrypting data, another application of cryptography is to generate hashes. A cryptographic hash function is an algorithm that deterministically maps data of arbitrary length to a number represented as a fixed length series of bits. And when we say that the algorithm is deterministic, all that we are saying is that it always produces the same output given the same starting point. So in this example, the word fox as input will always produce the number, here represented in hexadecimal form, starting with DFCD and ending with 2D17. And another important thing to note about cryptographic hashes is that they are also one-way compression functions, since they take in data of arbitrary length, can be any length, and produce outputs of a fixed length. So the fixed number of output possibilities gives rise to the possibility of collisions, and the collisions refer to the situation where identical hashes are generated from different inputs. And cryptographic hashes are used together with asymmetric encryption to implement digital signatures. And for the digital signature to be secure, the hash function needs to be collision resistant. Otherwise, it is possible to generate the same digital signature from different sources. So in this example, Alice generates a cryptographic hash of a message, encrypts that hash using her private key, and then sends the message together with the encrypted hash, which is now operating as a digital signature, to Bob. The recipient, Bob, can verify that the message was indeed signed by Alice because he knows a public key and uses it to check whether the message and the decrypted hash tally. So what we haven't covered here is how are public keys distributed and how they are verified with a person's identity. There's a whole infrastructure that needs to exist to support all that. But for today's purposes, it is sufficient for us to understand how digital signatures work and that they are used to secure systems like DNS, domain name systems, HTTPS, secure HTTP, and on blockchain systems as well that implement a distributed ledger to store transactions. And of course, we see an example here in the slide, which is to sign documents through the SingPass app. One could append one's signature to authorize certain transactions or documents that one might require, for example, to verify one's identity. And that's it. We are now at the end of today's presentation. I hope that it was instructive and helpful for you. I certainly hope that you go on to enjoy the rest of the seminar series. Thank you very much for spending your time with me. Bye.